Hi, we have already seen the monod equation, which is the equation which represents the relationship between the specific growth rate and the substrate concentration, which is basically a generalized equation, but there are specific kinetics derivations for the batch culture as well as for the continuous culture. In this session, I am going to talk about the kinetics of microbial growth in a batch culture. Batch culture, as we know, is a closed system. That means just like what we are doing in our laboratory, we have the medium. Once we inoculate the medium, we will put it in the incubator, and all the analysis will be done after the incubation. During the incubation, we are not adding anything to the medium, or we are not withdrawing anything from the medium. That's what a batch culture system is. In batch culture, there is no addition or no withdrawal of anything during the incubation period. In the batch culture, microorganisms basically follow typical phases of growth. First, they have the lag phase, then log phase, stationary phase, and death phase. I'm not going to explain the growth curve to you. You already know how a growth curve look like. One thing I want to say is that in a growth curve, the x-axis is time, y-axis is log number of bacteria. Log number of bacteria. If you draw a graph with the just number of bacteria, you don't get this. If you want to get this, it should be log number of bacteria. One more thing, it's actually the log number of viable bacteria, not the dead bacteria. So in this case, we are considering only the log number of viable bacteria. As I said before, bacterial growth has two different dimensions, or microbial growth has two different dimensions. One is grow in size, another is growth in numbers. In most of these kinetic studies, we are only including growth in terms of numbers, not in size. So that's a thing I want to share. In most of these graphs and derivations, we only see the number of bacteria, not the size of bacteria. One reason for that is that the growth of microorganism in numbers is more significant than the growth of microorganism in size. So this is the batch culture. In batch culture, actually, we have different kinetic derivations for each of these phases. But you can say the number of bacteria is pretty much constant in lag phase, and it is also pretty much constant in the stationary phase. But in log phase, there is an exponential increase in number of bacteria. In death phase, there is also a exponential decrease in number of bacteria, number of viable bacteria, indeed. So what happens in the lag phase? Lag phase, as you know, it's an adaptation period. There is no increase in the cell number, but there is an increase in cell size. Okay. As I said before, this graph is plotted with the log number of bacteria. That's why the line is pretty much straight. But in lag phase, what the bacteria do, bacteria actually preparing for the log phase, they preparing for the bacterial growth or exponential growth. In that time, actually there will be a increase in cell size, okay, but not in numbers. Okay, so in lag phase there is no increase in cell number, but there is a increase in cell mass. In bioprocess technology, sometimes the bacteria show dioxic growth. Dioxic growth means there will be multiple lag phase, one lag phase another after another one. Uh, Consider a situation in which we have more than two different carbon sources. One is glucose, then we have sucrose and starch. Okay, what bacteria do in this, out of these three sugar sources, the most easily utilizable sugar source is glucose. So first bacteria get adapted to the use glucose. Then once the glucose is depleted from the system, once the bacteria adapted to the glucose, it will grow and it will show a log phase. Once the glucose is depleted, then bacteria take some time to get adapted. They prepare the enzyme for utilizing sucrose. Okay, after the adaptation, again it shows another set of exponential growth. Okay, after sucrose is depleted from the medium, it need to get adapted to the starch. Okay, and once the adaptation phase is over, again it shows a log phase. So there will be multiple lag phase in a growth of microorganism. That's called a dioxic growth. So in lag phase, actually there is no growth of microorganism occurs, at least in terms of number. So we cannot actually calculate the kinetics of the growth. in lag phase. But in an industrial perspective, what we expect from a batch culture is that there should not be any lag phase. Okay, this lag node should not be there, or it should be the minimum. Because in the lag phase, there is no growth of microorganism occurs, there is no product formation occurs, so it's actually a dead time. So we want to avoid that. So all industrial practices are optimized to avoid or minimize the lag phase from the microbial growth. Okay, that's why we are using the seed fermenters to prepare the microorganism to before fermentation, so that the fermentation can begin instantaneously. Second, we have log phase. In this graph, you can see in the log phase, the microorganism will grow exponentially. Okay, there is a exponential increase in the cell number, and cell mass and number increase exponentially. Not only the number, the mass size of the microorganism will also increase, and that's why it's called a exponential phase. And exponential growth is a first order reaction. There is a direct relationship between the direct increase in the cell number. Mathematically, we can actually calculate the rate of growth, the specific growth rate, or dx by dt is equal to mu x. Okay, dx by dt represented the rate of growth. Okay, in t time interval, how much increase in the microbial mass occurs, which is equal to mu x. Mu, as we know, it is specific growth rate. X is the initial biomass. Okay, okay, t is the time, of course. Okay, so in a log phase, which is a first order reaction, in this reaction, the rate of change in biomass is given by mu x. Okay, mu is the growth rate, x is the biomass concentration. So it is like the rate of growth is influenced by the specific growth rate as well as the concentration. If the concentration is high, the number of cells is high, the growth rate will be high. If the specific growth rate, the capacity of microorganism to grow is high, this growth rate will be also high. So we can actually go for an integration of this equation. This equation we can go for an integration. After integration, what we get is equal is xt is equal to x0 e raised to mu t. Xt is the biomass concentration after t interval of time. Okay, if let's say if the t interval is 1 hour, after 1 hour, how much biomass increase has been occurred? So xt is the increase in biomass after t interval of time. Okay, x0 is the initial biomass. Okay, before this t time interval, how much was the biomass? Okay, if you have a if you are doing an experiment right now, you have the biomass right now is x0. Xt is the biomass after 1 hour, okay, or specific amount of time. E is the base of natural logarithm, mu is the specific growth rate, t is the time. So on integration of this equation, we get this xt is equal to x0 into e raised to x2. We can actually take the natural logarithm of this equation, then we will end up in ln xt is equal to ln x0 plus mu t. Okay, same same as this equation, ln xt is equal to ln x0 plus mu t. It's a equation for the straight line, as you know, y is equal to mx plus c. So in this, mu is the slope. Okay, the straight line will have a slope of mu, and the productivity is directly proportional to the mu. If the specific growth rate is high, the productivity will be high. So this is the derivation for the log phase of growth. Okay, in log phase, we get a straight line because ln xt is equal to ln x0 plus mu x plus t, and in log phase, the slope of this curve, the slope of the growth is given by mu, which is the specific growth rate. If the specific growth rate is high, the productivity will be high. So this is what we are talking about. This is the log phase. In this log phase, actually, if you take a close look at the bacterial growth curve, in the beginning of the log phase, we have an acceleration phase, and at the end, we have a decline phase. Further, the log phase is divided into 3 different stages. First is early log phase, mid log phase, and late log phase. Okay, Early and mid log phase is called balanced phase because there is a balanced growth is there. The substrate utilization and the growth is balanced, so we called early and mid log phase, maybe from here to here, is called balanced phase. The late log phase is called deceleration phase or storage phase or unbalanced phase. Okay, the late log phase is characterized by unbalanced phase. Okay, and after the late log phase we have a decline phase, it's a small time interval, and before the early log phase we have a acceleration phase. Okay, next we have the stationary phase. Stationary phase is basically a maintenance phase. There is no increase in the cell number or size of the viable number cells, but it is not a metabolically inactive state. Actually, the stationary phase, the microorganisms are very much active, but there is no growth. Okay, net growth rate is 0 because the growth rate is equal to the death rate. Okay, equal number of microorganisms will be born and equal number of microorganisms will be dead. Okay, and this happens due to the two different reasons, either due to the substrate limitation, unavailability of the carbon source, nitrogen source, minerals, vitamins, anything, or the toxin limitations. Microorganisms may be producing some toxins. Toxin in the sense maybe to produce a protein toxin, or sometime it produce an antibiotic, or it may produce some acids which inhibit the growth of the microorganism itself. So stationary phase, as the number of microorganisms is constant, there is no net growth. So we cannot make an equation for the stationary phase. Finally, we have the death phase. Just like the log phase, in the death phase, there is an exponential decrease in the cell number. So we can actually derive equation for the kinetics of the death phase. Here, the rate of death is Rd. Like in the previous equation, we say dx by dt. Here we can say maybe dd by dt, something like that. So anyway, Rd is the rate of death, which is equal to kdx. Okay. Kd is the specific depth constant, just like mu is the growth constant, so Kd is the depth constant, x is the number of viable cells. Okay, uh, so in this equation, the decrease in cell number is equal to the like death rate. If the death rate increases, the number of viable cells will be reduced. So Rd is actually equal to dx by dt in an inverse way. Rate of death is directly proportional to the is equal to dx by dt, which is in turn equal to the kdx. Okay, and this kd is a constant. Kd, which is as the kd for a specific condition is a constant, so x is equal to x0 e raised to minus kdt. Here you see the kdt has a minus in it because it is reducing the number of cells. Then we are taking the natural logarithm of the same equation. Then we will get ln xt is equal to ln x0 minus kdt. Okay, it is very much similar to the log phase of growth. Uh, Difference is like here we have kd instead of mu. The sign is minus, not plus. Okay, so ln xt is equal to ln x0 minus kdt is the derivation for the death phase. So that's a kinetics derivations for the batch culture. Thank you.